Welcome back to the deep dive. Today, we are doing something a little different. We're not just discussing the future of mobility. We're actually going to sit down at the drafting table. We're putting on the hat of a top-tier automotive engineering consultancy. And our task, your task, is to write the definitive rulebook for the next generation of ultra-efficient electric vehicles.
And that rulebook has a name. It's the Engineering Requirements Specification, or the SOR.
Hmm.
And this isn't, some high-level market analysis. This is prescriptive nuts and bolts engineering. We're using McKinsey-style structured thinking, and you, the listener, are acting as the chief systems engineer today. Our mission is to deliver a complete non-negotiable blueprint for the energy management system, the EMS, of a brand new micro-low-speed electric vehicle and LSEV.
And the context for this whole project sounds, well, brutally unforgiving. We're trying to engineer cutting-edge efficiency, the kind of performance that usually comes with these massive budgets and luxury price tags. But we're doing it for a market segment where every single dollar, every single gram of weight is absolutely critical to survival.
That is the core conflict. It's what our source material calls the dance in chains. It's a fantastic phrase. We are forced, on one hand, to achieve global regulatory compliance and really high efficiency. That demands sophisticated software, robust monitoring, and on the other hand, we have to stick to these extreme, almost impossible cost targets. Our entire job today is to bridge that massive gap between these mandatory standards, especially the ones coming out of Asia and Europe, and the hard reality of very low-cost LSEV hardware.
Okay, so our main source is a deep strategic technical report. It covers everything from international regulations all the way down to the nitty-gritty of control logic. So before we even think about the first component, you're saying we have to define the geopolitical landscape. Why does regulation, which most people see as just, bureaucratic paperwork, actually dictate the fundamental engineering choices we make from day one?
Because if we fail to comply, the product is dead on arrival. It's that simple. If we miss the mark on these regulations, we are barred from sales. We lose the crucial tax exemptions that make these vehicles affordable in the first place. We absolutely have to define these non-negotiable legal and market boundaries before the first line of code is written or the first wire harness is even designed.
And it sounds like the regulatory earthquake that's shaking this entire segment is happening in China. Specifically, a new standard, GB 36980.1 2025. It takes effect January 1st, 2026, and our report flags it as the single most critical engineering constraint we're facing.
It's the ultimate boundary condition. I mean, this Chinese standard is the world's first legally binding energy consumption limit for EVs. It's not a suggestion. It imposes a clear mandatory cap. For example, for heavy electric vehicles, the ones around 2 tons, the baseline cap is set at 15.1 kilowatt hours per 100 kilometers.
Right, but our focus, the LSEV, is in this light vehicle category. We're talking 800 to 1,000 kilograms. So how do we apply that 15.1 number to our much lighter vehicle?
The standard uses a strict proportionate limit. It's often calculated through linear interpolation based on the vehicle's mass. This becomes our LSCV red line. If our specific vehicle fails to meet this proportionate limit, 2 things happen instantly. First, it can't get the necessary government announcement, which means you cannot legally sell it in China, period. Second, it automatically loses the purchase tax exemptions, making it completely non-competitive.
Okay, so losing access to the world's biggest LSEV market and destroying the entire economic model. That sounds like catastrophic failure. So what is the aggressive, proactive engineering target we need to put in our SOR right now to make sure we clear that red line comfortably and get all the incentives?
Okay, based on the proportional limits for our target mass, the SOR must mandate an efficiency target below 10 kilowatt hours per 100 kilometers. That's measured on the China Light Duty Vehicle Test Cycle, the CLTC. This number, sub 10, is the strategic performance anchor for the entire project.
Let's put that in perspective for a second. Our source report notes that the existing, the really successful market leaders, the gold standard right now, things like the Wuling Mini EV, they're currently getting figures somewhere between 9 and 11 kilowatts per 100 kilometers.
Exactly, which means we're not just trying to meet the minimum, we have to out-engineer the current champions.
Yeah.
This new standard, effectively, it mandates something like an estimated 11% efficiency gain over what is already mass-market best-in-class performance.
Wait, I have to challenge that. If we need an 11% efficiency gain, why aren't we just mandating more expensive hardware? Better aerodynamics, a heat pump, lighter materials. Why are we trying to get this critical 11% purely from software controls?
That's the dance in chains, right there in action. We're completely budget constrained. The marginal cost of a premium heat pump or, say, exotic materials would price us out of the LSEV market entirely.
It's a non-starter. The hardware, the motor, the battery pack, it's already optimized for extreme low cost by the supply chain. So that 11% gain has to be extracted through smarter management of the existing power flow. This means it is fundamentally a software mandate. We need extremely sophisticated strategies like precise regenerative braking profiles, active coasting logic. It's all driven by regulatory physics.
Okay, that sets an incredibly high bar for performance. Now, let's shift over to Europe. Here we enter the world of L6E and L7E quadricycle regulations, which it seems are defined less by efficiency and more by these hard, literal, physical, and speed constraints.
That's correct. For the L6E, the light quadricycle category, the constraints in our SOR have to be very precise. Maximum speed limit of 45 kilometers per hour and a power cap of 6 kilowatts. And our engineering team must ensure the EMS includes an untamperable software speed limiter. This isn't just a setting. It has to be a core protected function, probably locked in read-only memory to ensure compliance.
And for the heavier L7E class,
The L7E lets you have more power, up to 15 kilowatts, but it hits you with these really punishing weight restrictions. 450 kilograms for passenger version, 600 for cargo. And critically, that weight limit is excluding the mass of the battery. This aggressive weight limit directly forces our hand on the voltage platform decision because we have to save every single gram of copper we can. We'll get to that.
the report also brings up a sort of forward-looking safety requirement in Europe, which is being pushed by past criticisms from Euro NCAP about the low crash safety of these vehicles. We can't ignore future liability.
Exactly. There's increasing pressure, both from consumer safety groups and from, future regulation prediction models, to bring functional safety standards closer to what you see in passenger cars, the M1 class. So to mitigate our product liability risk, our SOR must address ISO 26262 functional safety. We have to aim for at least ACEL A or B for all the critical powertrain functions, especially torque safety monitoring.
Okay, specifying ACEL A or B, what does that actually mean for the hardware? What does that cost us?
It means we can't just rely on a single cheap microcontroller to handle the accelerator pedal and deliver torque. It's not allowed. We have to introduce redundancy. We need monitoring hardware, a watchdog chip, specifically to verify that the main controller is operating safely. And that is a direct cost increase for our VCU, which we have to account for in our budget targets from day one.
Okay, so let's define the global efficiency goalpost. Japan's micromobility segment seems to offer the benchmark figure that, if we could hit it, would guarantee massive success.
The benchmark, yes. The aspirational goal, really, is the Toyota C+ pod. It achieved an absolutely astonishing 5.3 kilowatt hours per 100 kilometers. That's 53 watt hours per kilometer.
Hang on, 5.3, that is literally half the energy consumption that we're mandating just to clear the Chinese regulatory bar. That is a massive performance gap. What specific technical decisions allowed them to get to that level of ultra efficiency?
Well, the primary decision was a smaller, lighter package overall and just extremely aggressive power management. They maximized the operational temperature band for the battery, and they highly optimized the motor efficiency map, which is something we absolutely must emulate in our dyno testing phase. And on top of that, the Japanese market is moving from the older, gentler JC08 cycle to the more transient WLTC cycle. That demands higher EMS control precision, especially in dynamic situations. This reinforces our need for things like EKF algorithms and very precise VCU control.
Okay, and finally, the U.S. market with its low-speed vehicle, or LSV category.
Yeah.
This seems to impose a very simple but very restrictive federal speed cap.
It's absolute. Federal law says maximum speed is 25 miles per hour, which is about 40 kilometers per hour. So for our SOR, this means the EMS specification must include robust measures to ensure that cap cannot be bypassed. We must mandate either geofencing, where the speed is limited based on location, or a really robust hardware locking mechanism, something that physically or digitally prevents the user from modifying it for higher speeds on public roads. Given the liability in the U.S. market, tamper-proofing is a critical legal requirement.
So part one really establishes the core conflict. China is demanding unprecedented efficiency, and they're forcing us to do it with software. Europe is demanding hard speed limits and safety redundancy, adding costs with ACEL AB. And the U.S. demands tamper-proofing. The entire engineering spec is basically being dictated by this global regulatory friction.
Exactly. And with those demands now defined, we can pivot to the architecture. We have to make these big strategic decisions on the voltage platform to execute those mandates, while at the same time satisfying these ruthless cost and weight constraints. And the choice of voltage, it affects everything: wire thickness, material cost, heat loss, and ultimately our ability to comply with that GB 2026 standard.
Okay, let's start with the low voltage options. They seem appealing for their simplicity, right? Things like 48-volt or 60-volt systems like you see in the Citroenami. What's the seductive draw of low voltage, and why do we ultimately have to reject it?
The draw is, as you said, safety and simplicity. Anything below 60 volts DC is generally considered touch safe. Maintenance is simpler. You don't need specialized high voltage training for technicians. But physics is our enemy here. The relationship is power equals voltage times current.
So if the voltage is low, the current has to be really high to deliver the same amount of power.
Exactly. And to get the propulsion power we need, the current becomes extremely high. And high current means high material cost and significant losses. It requires much thicker copper cables, which dramatically increases the cost of the wiring harness. And critically, it increases the vehicle weight. That's a death sentence for meeting those L70 weight limits we just talked about.
And the high current also drives inefficiency through just raw heat.
Precisely. The power loss due to resistance, what we call I2LR law, is much, much higher. This translates directly into significant heat generation and, most importantly, lower overall system efficiency. And that lower efficiency is functionally incompatible with our GB 2026 target of below 10 kilowatts per 100 kilometers. The efficiency loss alone makes 48V a non-starter for our platform.
Which pushes us unequivocally toward a high-voltage architecture. Specifically, the report recommends 96V to 150VV. It sounds like we're trading some electrical complexity for big material cost savings.
That is exactly the trade-off. By adopting a 96V to 150V nominal platform, the current drops dramatically. Lower current lets us use thinner wiring harnesses that directly reduces our copper cost and our vehicle weight. And most critically, it offers the higher system efficiency we need to deliver on that mandatory 11% gain for GB 2026.
And crucially, we're not inventing some brand new technology here. We're leveraging existing supply chain.
Absolutely. The 96V and 144V architectures are extremely mature, especially within the massive Chinese EV supply chain. This gives us the cost leverage we need and reliable component sourcing. Therefore, SR Decision 2.1 mandates a 96V to 144V nominal voltage high voltage architecture. This is the optimal strategic balance: efficiency for compliance, cost savings on copper, and supply chain maturity.
Okay, once we've defined the voltage, we move to the controller topology. The traditional EV architecture, it separates the vehicle control unit, the motor control unit, and the BMS into 3 or more separate boxes. For an LSEV, that just sounds like a huge waste of resources.
It is entirely too heavy, too complex, and way too costly. A traditional distributed architecture adds redundant casings, connectors, cooling hardware. The trend, and it's driven by this ruthless pursuit of cost reduction, is all-in-one integration. We're talking about consolidating systems, 3-in-1 units that integrate the E-motor, the reducer, and the MCU, or even 5-in-1 systems that go further and integrate the PDU and VCU.
So how do we specify this integration in our SOR while still maintaining that necessary functional safety separation that ACEL AB requires? We need logical separation, even if we have physical consolidation.
That is the key engineering challenge. So we define a very specific, recommended logical versus physical split. On the physical layer, we mandate integrating the VCU control logic code directly onto the MCU's high-performance microcontroller. We can use powerful, readily available chips for this, like something from Infineon's Artix family.
So we're essentially just eliminating one physical box entirely by having the VCU software run on MCU's brain.
Precisely. They share the same cooling system, the same casing, the same power source. Eliminating just one full ECU node is a cost saving of potentially over $100 per vehicle. That's huge in this segment. This is physical layer integration.
What about the battery management system, the BMS? We need that core monitoring function, which is so critical for fire safety, to remain completely uncompromised.
The BMS is different. For absolute functional safety, especially protecting against overcharge and thermal runaway, its core monitoring hardware, the analog front end or AFE, must remain physically independent. That's the part that directly measures the cell voltages and temperatures. However, the complex high computation algorithms like the state of X calculations, state of charge, can be moved. They can run on the much stronger integrated VCU-MCU domain controller. This is the logical layer integration. We're leveraging the VCU's superior computing power to run the complex extended Kalman Filter model we're going to need.
With our consolidated hardware defined, let's talk communication. We need speed and reliability for the powertrain.
The SOR has to mandate a robust dual-bus communication network. CAN is the industry standard here. CAN Bus 1 is our high-speed link running at 500 kilobits per second. This is dedicated entirely to critical powertrain communication. The integrated MCU-VCU, the BMS, and the onboard charger. And we must specify that this bus has to fully support the GBT 27930 charging protocol, which defines that complex handshake required for the Chinese charging infrastructure.
So if the BMS wants to immediately cut the charging current because it's too cold, that high-speed CAN bus is the pathway for that critical safety message and the rest of the car.
Everything else runs on a separate lower-speed CAN bus too, typically 250 kilobps. It's for less critical body and chassis systems, things like the instruments, climate control, electric power steering. And furthermore, we reserve the LM bus for ultra-low-cost peripheral things like simple window controls or door locks where data speed and bandwidth are totally irrelevant. This logical separation simplifies diagnostics and ensures high-priority safety messages are never delayed.
All right, part 3. This is where the magic happens and where we have to earn that crucial 11% efficiency gain that the GB 2026 standard demands. Since the hardware is optimized for cost, the vehicle control unit, the VCU software, is our efficiency engine. Let's start with managing the driver's input, torque management, and pedal maps.
The VCU must define specific pedal maps, and that's because the way the driver interacts with the accelerator is often the biggest source of energy waste. We have to mitigate driver impulsiveness through software.
So we must mandate specific driving modes, starting with the non-negotiable default for an LSEV Eco mode. How do we define its characteristics in the SOR to just absolutely maximize efficiency?
Eco mode is the engine of compliance. It prioritizes range above everything else. The VCU has to implement an S-shaped pedal curve. This is crucial because it drastically desensitizes the pedal in the initial phase of travel. For example, the first 50% of the driver's pedal movement only yields, say, 20% to 30% of the motor's available torque.
So we're essentially filtering out all those inefficient, jerky accelerations that just waste energy and generate heat. It makes the car feel slower to respond, but it's incredibly smooth and efficient.
Exactly. It forces a gentler driving style without the driver even consciously trying. And beyond the pedal map, we impose hard limits. We limit peak power to 70% of the motor's rated power. This controls current draw, protects the battery from thermal stress, and we also mandate VCU integration with the HVAC system, forcing an Eco-AC mode that actively reduces the power draw of the compressor.
Okay, normal mode is the balance, a standard linear torque response. But sport mode, that's included purely for driver perception, right?
Sport mode is performance theater, exactly. It uses a highly logarithmic map, so even a light tap on the pedal provides a really rapid, high initial torque response. It makes the car feel quick. We allow the motor's short-term peak power, assuming the thermal system can handle it. And critically, we specify the sport mode has to reduce regenerative braking to give a greater sense of traditional vehicle coasting.
And that transition-reducing regen in sport mode leads us directly to the great EV efficiency debate. Adaptive regenerative braking. I think everyone assumes that one-pedal driving is the gold standard for range, but our report suggests the opposite is actually true in some conditions.
The report delivers a critical verdict on this, and it's especially relevant for LSEVs. Coasting, that's zero torque, is often more energy efficient than strong regeneration followed by reacceleration, particularly at higher speeds. This runs completely counter to a lot of EV wisdom, but it's just pure physics.
Okay, let's spend a moment on the why there. Why is simply maintaining inertia, which generates zero energy, better than recapturing it?
It all comes down to conversion losses. When you regenerate, you convert mechanical kinetic energy into electrical energy in the motor. Then you store that as chemical energy in the battery. And then later, when you accelerate again, you convert chemical back to electrical and back to mechanical.
That round-trip efficiency is typically only around 70%. So if a driver is constantly oscillating between strong regen and then re-accelerating, you're cycling energy through that lossy system over and over. If you can just maintain speed and coast, you avoid that 30% loss entirely.
So the VCU can't just have a simple fixed regen setting. Our SOR has to mandate adaptive logic.
Absolutely. The VCU has to be a sophisticated traffic manager. At high-speed liftoff, the VCU immediately enters coasting mode, 0 Newton-meters of torque, to leverage inertia and avoid that conversion loss. Conversely, in low-speed or city driving, when you lift off, it enters a moderate regenerative braking mode to simulate traditional engine braking and maximize energy recapture where you know stopping is inevitable.
And beyond efficiency, aggressive regeneration can introduce a major safety problem in these short-wheelbase LSEVs.
Yes, and this is a functional safety constraint that links right back to our ASIL requirements. LSEVs are susceptible to what engineers call transient instability. It's a higher-risk tail-wagging scenario if you apply aggressive regen too quickly to the rear wheels. It can cause a skid. So the SOR must require that the regeneration torque drops to 0 N-meters within a mere 10 milliseconds if the wheel-slip ratio exceeds a low threshold, say 15%, or if the ABS system activates. That is a crucial, measurable safety KPI.
The 10-millisecond window really confirms just how high performance that VCU chip needs to be. Okay, finally, we have to define the ultimate safety net. Derating protection, or limp home mode, to protect the low-cost hardware when it's under stress.
We need to define strict, hard limits to protect the longevity of our most expensive components. So for thermal derating, we specify 3 mandatory trip points. If motor temp exceeds 110 Celsius, the VCU begins a linear torque reduction. If it hits 130 Celsius, output torque has to be reduced to 0. Similarly, the battery needs protection. If its temperature goes over 45 Celsius, the VCU has to limit the maximum discharge power to prevent long-term degradation.
And what about that critical moment when the battery is almost completely drained?
That's the low SOC derating for limp home mode.
Yeah.
If the state of charge drops below 10%, the VCU implements drastic measures. It caps the maximum speed severely down to 30 kilometers per hour. And critically, it forces the closure of high-draw systems like the AC heater. The only auxiliary function that must be preserved is basic safety, like defogging. This ensures the remaining energy is entirely dedicated to moving the vehicle safely to a charging location. It minimizes the chance of stranding the user.
All right, we've established that the VCU control is our efficiency engine, but the VCU is effectively blind without highly accurate data from the battery management system. For cost reasons, LSEVs rely on lithium iron phosphate, or LFP, chemistry, and our report flagged a huge problem with this, the SOC estimation crisis.
LFP is the cost champion, absolutely, but it poses a unique technical headache. The crisis is this. The LFP battery's open-circuit voltage curve, the OCV curve, is incredibly flat across something like 80% of its usable range, specifically between 15% and 95% state of charge. The total voltage change across that massive range is often just a few millivolts.
So using simple voltage lookup tables, which is the classic way to tell a battery's percentage, is functionally useless. It's like trying to tell how full a massive water tank is by looking at a tiny flat gauge on the side.
That is the perfect analogy. The moment a heavy current is drawn or regenerated, the voltage jumps or dips, and the BMS instantly loses its reference point. This leads to massive, unpredictable fluctuations in the reported range. It creates extreme range anxiety for the user and risks unwarranted limp home activations. Therefore, the SOR must mandate moving beyond simple current integration.
Okay, so the technical solution mandated in the SOR is the extended Kalman filter, or EKF. This sounds like highly complex control theory. How did the EKF practically solve this LFP accuracy problem for the average driver?
EKF is a sensor fusion algorithm. It intelligently merges two data sources. First, it uses the short-term accuracy of what's called Coulomb counting, just integrating the amps in and out. Second, it uses the stability and predictive power of a detailed, physics-based equivalent circuit model, usually the Thevenin model. This model predicts what the terminal voltage should be based on the known currents and temperatures.
And the magic is in the correction step, I'm guessing.
Exactly. The EKF constantly measures the difference, the residual error between the model's prediction and the actual measured voltage from the AFE hardware. It then uses that residual error to dynamically correct the estimated SOC value. This process continually eliminates the systematic accumulating error that plagues simple current sensors, ensuring accuracy even when that voltage curve is flat.
This sophistication is non-negotiable for compliance. What is the KPI we have to set for SOC accuracy in our SOR?
We have to hold the line rigidly here. The SOC estimation error must be less than 5% over the vehicle's full lifetime and across the entire operating temperature range, from -20 C to 55 C. This low error is fundamental to maximizing the vehicle's usable range, which is essential for hitting our competitive targets.
Okay, moving from estimation to safety. The most critical battery risk, especially in cold climates, is low-temperature charging.
This is a major hazard for all Li-ion chemistry, but it's especially relevant for LFP because that flat voltage curve makes temperature control tricky. Charging any Li-ion battery below 0 degrees Celsius causes lithium plating. Metallic lithium deposits permanently on the anode. This leads to irreversible capacity loss and, critically, a severe permanent fire risk from microscopic internal short circuits.
So the BMS has to act like a hard security guard, just shutting down the entire process if the temperature drops below freezing.
It requires a three-step mandatory logic in the SOR. First, the hard stop. When the minimum cell temperature, Tmin, drops below 0 C, the BMS must instantly request 0 amps from the onboard charger. It's a physical and digital block. Second, if the vehicle has PTC heating films, which we should really mandate for cold weather markets, the BMS has to prioritize heating the battery pack using the charging station power before allowing any charge current into the cells.
And what about the actual charging profile between freezing and the optimal temperature? We can't just slam it with full power at 1 degree.
No, we have to implement a controlled step charging profile. We gradually increase the current as the temperature rises. For example, we mandate a very slow rate, say 0.1 C, for temperatures between 0 and 5 degrees. This increases to 0.5 C when the temperature is between 5 and 15 degrees. And only when the temperature is above 15 C can we safely use the maximum rate of 1 C or more to minimize charge time.
Okay, finally, cell balancing. Given our extreme cost constraints, we have to choose the simplest, cheapest technology.
And that mandate points directly to passive balancing, using what are called bleed resistors. This system simply burns off excess energy from the highest charged cells as heat to bring them down to the level of the lower cells. It's not energy efficient, but it's the only cost-effective solution for LSEV.
So passive balancing is essentially just venting the pressure from the highest charged cell by turning its excess energy into tiny bits of heat. It's the cheap, simple way to maintain balance.
That's it exactly. Our SRR needs to specify the balancing current must be low, between 50 and 100 milliamps. And critically, the activation logic must be tightly controlled. Balancing should only activate when the cell voltage is high, say above 3.4 volts, and the voltage difference between cells exceeds a threshold like 30 millivolts. This ensures we aren't just wasting energy during normal driving, but only performing the necessary maintenance to ensure long-term pack consistency.
All right, we've specified the high-level brain. Now let's address the physical systems. Thermal management, the TMS, is where LSEV cost-cutting is most visible. Liquid cooling is too expensive, so the entire strategy rests on optimizing air cooling.
Air cooling is cheap, simple, but it is highly inefficient, and it can lead to terrible temperature variations across the battery pack. Our SOR has to define strict physical and control requirements to fight this inherent inefficiency. If we fail, the maximum temperature difference, the delta T, across the pack will balloon, the hottest cells will degrade faster, and the usable life of the vehicle will just plummet.
Let's start with the control logic for the fans. We can't have them clicking on and off constantly. That's both really annoying for the driver and inefficient.
That rapid on-off is called short cycling. The solution is using PWM-controlled fans paired with hysteresis in the control algorithm. Hysteresis builds a necessary gap between the turn-on and turn-off points, so we mandate specific thresholds. The fans start at a low duty cycle, say 30%, when the max temp exceeds 38 Celsius. They ramp up to full speed at 48 Celsius, but crucially, they don't shut off until the temp drops all the way down to 33 Celsius. That 5-degree thermal window prevents the fans from switching on and off every few seconds. It makes the system predictable and quiet.
But clever software isn't going to fix bad airflow inside the battery pack. How does the SR mandate physical design to ensure even cooling and minimize that delta T?
The physical design has to prioritize flow field optimization. We mandate structures such as J-shaped or U-shaped flow paths with internal disturbance structures, which are known as turbulators.
What's the practical benefit of these structures? What's a turbulator?
They force the air to mix violently, which is exactly what we want. Air cooling fails when a static boundary layer of air forms right next to the cells. These turbulators, they break up that boundary layer, which significantly improves the heat exchange coefficient. And the ultimate KPI for this physical design, which has to be verified in Part 6, is ensuring the maximum internal battery temperature difference, that delta T, is kept within 5 degrees Celsius. If it exceeds 5 degrees, the degradation rate of the hottest cells will far outpace the others, leading to a much faster overall pack capacity drop.
Okay, now let's circle back to functional safety. ISO 26262. We know we can't afford the highest level ASIL D, so we need to focus on the 2 highest risk hazards that demand ASIL B or C compliance.
We use smart risk decomposition. Hazard 1, unintended acceleration. This is a critical product liability risk. The solution is to mandate a 3-layer e-gas monitoring architecture.
Okay, can you explain those 3 layers for me?
Layer 1 is the main VCU, computing the torque request based on its pedal sensor input. Layer 2 is the safety net, an independent, low-cost monitoring chip, the watchdog, that reads the accelerator pedal signal separately. It then verifies the VCU's computed output against its own independent reading.
And what triggers the safety response?
If the deviation between the VCU's computed torque request and the independently monitored pedal signal exceeds a tightly specified tolerance, let's say 5%, the monitoring chip must take autonomous action. And that action, layer 3, is to directly cut power to the main high-voltage contactor. It overrides the main VCU and shuts down propulsion entirely. This prevents the car from accelerating uncontrollably.
Okay, hazard 2, high voltage electrical shock. And this risk is amplified because we chose the 96V to 144V architecture.
Right, the required safety integrity level for this is ASIL D, and the solution is the mandatory implementation of the high-voltage interlock loop, or HVIL, in all high-voltage connectors.
So the HVIL is basically a tripwire running through the connector sheathing. It's a physical failsafe that uses low voltage to protect us from high voltage.
That's the perfect description. It's a low-voltage circuit that must remain closed for the high-voltage system to operate. If that low-voltage HVIL circuit is broken, say, a technician removes a cable during maintenance, or a connector is damaged in a crash, the BMS has to immediately detect the break. Its mandatory action is to open the main contactor and discharge the entire high-voltage bus to below the 60V safety limit, all within 200 milliseconds. This is a hard, measurable safety requirement in the SOR.
Finally, we have to ensure our charging system actually works in the Chinese market, which means strict adherence to the GBT 27930-2015 standard. This involves a complex communication handshake.
It's a sophisticated, multi-state communication protocol between the vehicle and the charging station. We have to embed the critical dynamic requirements into the SOR. During the parameter configuration stage, where the BMS sends its BCP message, the BMS cannot send fixed, simple values for maximum voltage and current.
It has to calculate those values dynamically based on real-time conditions.
Exactly. Based on the current cell temperature to prevent that lithium plating and the precise state of charge, the BMS must dynamically calculate and send the maximum allowable voltage and current to the charging station. If the battery is cold, it sends a lower current request. If the battery is almost full, it adjusts the voltage request. And we also need to optimize the constant current, or CC, phase. The EMS has to precisely monitor the battery terminal voltage, compensating for all the wiring losses, to extend that high-power constant current phase as close to 100% SOC as possible before it switches to the slower constant voltage phase. This maximizes charging speed.
We have established an incredibly detailed blueprint. We've covered everything from global regulatory limits down to millimeter-level airflow. Now, as the Chief Systems Engineer, we have to define the V-model verification process, the comprehensive validation plan that proves our EMS actually meet every single requirement we just mandated.
The V model ensures we catch errors early where they are cheapest to fix. We start far to the left on the V with abstraction. MIL, model in the loop. This is algorithm verification in a simulated environment, usually MATLAB Simulink. We verify that our core logical models, the EKF SOC model, the thermal hysteresis logic, the adaptive region strategy, that they all work mathematically under ideal simulated conditions.
Okay, so once the math is proven, we move to testing the actual physical brains of the system, the VCU and BMS chips, before they're even in the vehicle.
That's HILO, hardware in the loop. Using specialized testing platforms like DSpace or Vector, we test the actual electronic control units against simulated extreme fault conditions in real time. We need to throw simulated disasters at it. A pedal sensor open circuit, a massive CAN bus storm, a sudden charging communication failure. The main goal here is to verify that our functional safety logic, that eGas watchdog's 5% deviation and the 10 meters regen cutoff, that they work reliably on the actual production hardware.
After Hill validation, we put the integrated powertrain system into a full driving environment.
That's dyno testing on a chassis dynamometer. This is crucial for energy efficiency compliance. We run the vehicle repeatedly through the mandatory CLTC and WLTC drive cycles, and we specifically use the dyno to calibrate the motor efficiency map and optimize the blending point between regenerative braking and the physical friction brakes. This is really the last chance to ensure we achieve that sub-10 kWh at 100 km target under the exact regulatory conditions before we commit to mass production.
And finally, real-world validation to ensure robustness across all possible environments.
Road testing. This is the final sign-off. We have to mandate full validation cycles. This includes summer high-temperature tests to really push the limits of our air cooling strategy and verify that 5-degree delta T KPI, and winter low-temperature tests to verify the low-temp charging safety block and accurately quantify the vehicle's range decay in adverse conditions.
And now for the most sobering reality check, cost engineering. All of this required sophistication. The EKF, ASIL-B monitoring, the integration, it all has to fit within these razor-thin LSEV BOM targets. The SOR has to set aggressive but achievable cost limits based on 2025 market forecasts.
The cost constraints are absolutely non-negotiable. For the LFP battery pack, which will be between 10 and 15 kilowatt hours, the target has to be between $800 and $1,100.
Let me just put those numbers in perspective. If we hit the low end of that, an $800 battery target, we're talking about the single most expensive component in the entire vehicle costing less than some people spend on a high-end smartphone. That razor-thin margin really explains why every previous decision from 96V to an integrated VCU was so necessary.
Precisely. That target reflects an aggressive cell cost of about $60 to $70 per kilowatt-hours. It forces us to leverage massive scale from suppliers like CATL, Goshen, or EVE. Next, the 3-in-1 eDrive assembly, about 20 kilowatts for an LSEV, that must target $350 to $500. High integration is the single most important factor there.
And the VCU BMS hardware, which we've just burdened with the highly complex EKF and functional safety requirements.
The combined VCU BMS hardware target has to be extremely low, $80 to $120. And this is only achievable by leveraging mature, domestic automotive-grade MCUs like the GigaDevice GD32. Using these cost-effective chips while demanding high performance is the key cost optimization for the EMS brain.
And finally, the charging unit.
The onboard charger, the OBC, and the DC-DC converter are typically integrated into a 2-in-1 unit. Given the standard 3.3 kilowatt OBC for LSEV, the cost target for that integrated unit is $150 to $200.
A modern platform also needs to be serviceable and updatable out in the field. What are the mandatory communication and diagnostic requirements?
The SRR has to mandate that the system is FOTA, firmware over the air, ready via CAN bus software flashing. This allows us to push efficiency or safety updates remotely, avoiding costly dealer recalls. And furthermore, the system must fully support UDS protocols, ISO 14229, for standardized dealership diagnostics. This means supporting commands like read DTC, clear DTC, and read data stream for remote monitoring. This standardization is essential for long-term serviceability.
So we've successfully completed the engineering requirements specification. We've moved from global law all the way down to the precise millivolt level control logic required for an ultra-efficient LSEV. We defined a 96V architecture. We mandated EKF for LFP. We specified ESLB monitoring. Let's summarize the 3 most important strategic takeaways for the engineering team.
Okay. First, the strategic imperative is clear. Software is the edge. Since the hardware costs are basically fixed by this mature, low-cost supply chain, the only possible way to squeeze out that crucial 7 to 10% extra efficiency for GB 2026 compliance is through superior control software. This means mandating sophisticated algorithms like the EKF for SOC, the adaptive regen logic where coasting is better than regen at speed, and smart thermal management. Software defines our competitiveness.
Second, the architecture has to be inherently adaptable to different geographies.
We must embrace platform thinking. We designed a single EMS platform that's compatible across both 96V and 144V. This flexibility allows us to easily adapt to radically different market needs. Switching between L6E speed limits in Europe, the 25-mile-per-hour US limit, and higher L7E power demands, just by changing software parameters, not expensive hardware. This flexibility saves massive NRE costs.
And third, the lesson that's often learned too late, which we've tried to mitigate by writing this SOR, compliance.
Embrace compliance early. The financial cost, the development timeline catastrophe of trying to retrofit systems to meet the complex GBT 27930 charging protocol, or introduce ISO 262622 safety late in the development cycle is prohibitive. Compliance, especially for safety and efficiency, must be baked into the system's DNA from day one, and this SRR provides the non-negotiable framework to do exactly that.
So we've successfully engineered a robust EMS designed to meet that required 10 kilowatt-hour per 100-kilometer target. We've secured compliance and competitiveness in the current regulatory environment. But the micromobility sector is moving incredibly fast, and as chief systems engineers, we have to look beyond the immediate hurdle.
And that's the final point. Given the rapid and aggressive evolution of global standards and the fact that we have spent this deep dive detailing the engineering needed to meet the current regulatory red lines, we have to ask the final provocative question. We know the Toyota C+ pod achieved an ultra-low 5.3 kilowatt-hours per 100 kilometers. So if the next round of global standards demands we approach that figure, does achieving the C+ pod's level of ultra-performance represent the strategic imperative for survival in the next decade of micromobility, rather than just merely meeting the mandatory minimums of today? That is the efficiency challenge of tomorrow.